Okay guys, let's move on to question number 11. So this concept is the same as we did before, Hess's law. So we have to sum up those two equations to get this equation over here. So let's look at this equation and what it doesn't have. So we have NO, O2, and NO2. Here we have NO, NO2, and O2, and O2. But we don't have O3 in this equation, but we have O3 up here. So we have to cancel O3. However, we have to do two steps to be able to cancel O3. First of all, those two are, the O3 are on the same side. So we cannot cancel them if they're on the same side. So we have to decide one of the equations to switch them. Now, which equation are we going to switch? Let's look at it. O2 here is found on the right side. However, it should be found on the left side. NO is already on the left side and it stays on the left side. So of course, we're going to have to switch the first equation. So let's reverse the first equation. We're going to have 3O2 gas gives us 2O3 gas also. And if we reverse the equation, we have to change the sign of delta H. So it was minus 427 kilojoules. It's going to be plus 427 kilojoules. Okay? Now let's look at the second equation. Now we only have one O3 molecule. However, here we have two O3 molecules. So we have to multiply our entire second equation along with the enthalpy by 2. So what are we going to get? We're going to get 2NO plus 2O3 gives us 2NO2 plus 2O2. And now delta H is going to be minus 122 times 2, which is going to be 244. So minus 244 kilojoules. Now we can basically cancel our equations. So we can cancel O3 and O3, and we're going to add up both our equations along with their enthalpies. So what will we get? We will get 2NO, not 2NO2, plus, now we have 3O2 here and we have 2O2 here. So we're going to cancel. We'll just have one remaining O2, which gives us 2NO2. And our enthalpy for this equation will be, we have to sum up 427 minus 244, and we will get 183 kilojoules. However, are we done? No, we are not done yet. Why? Because the final equation has one NO and not two NO, and it has one NO2, not two NO2, and it has half O2, not one O2. So how are we gonna go from here to here? We basically divide by 2. We divide everything by 2 along with our enthalpy change. So we will get NO plus half O2 gives us NO2, and then our enthalpy change will be 183 divided by 2 is going to be 91.5 kilojoules, and don't forget it's going to be positive. And since they said 3 significant figures, so we're gonna keep it as it is, 91.5 plus 91.5 kilojoules. Let's move on. So calorimetry is the measurement of, as we said before, it's the measurement of the heat content of a substance. Okay, to change the temperature of a particular calorimeter and the water it contains by 1 degrees requires 5 kilojoules. The complete combustion of 7 grams of ethylene gas in a calorimeter causes a temperature rise of 5 degrees Celsius. They're asking us to find the heat combustion. So there's two things to know. Since they said heat combustion, our final answer should be negative. And we're going to account for that in this formula. So the formula for delta H is going to be Q over N minus Q over N. However, this Q is not, this Q is not going to be the specific heat capacity. This is just going to be the heat capacity. Now, what's the difference between them? Heat capacity, we find it by doing C times delta T over N. However, specific heat capacity is going to be MC delta T. However, here we are not given the mass. So this is a small trick you guys can follow. If you're not given the mass, find the heat capacity and not the specific heat capacity. But if you want to understand why, the specific heat capacity is usually the measurement to raise 1 gram of a substance, so 1 gram of a substance by 1 degree Celsius. However, in the heat capacity, we do not account for the mass of the substance. So let's continue with the equation. So C is 5 kilojoules. I can write it as 5 times 10 power of 3 times the change in temperature. Since it's the change, it doesn't matter if the temperature is in Kelvin or in Celsius. So times 5 over. To find moles, what can we do? Mass over molar mass. They already gave us the molar mass of the substance, so 7 over 28, so 7 over 28, and then don't forget the negative sign, which I already put in the beginning, and we will get 25,000. So let's first find the number of moles. 7 divided by 28 is going to be 0.25, so 0.25, and then I will have 25 times 10 power of 3 over 0.25, and we will finally get the answer as 100 kilojoules. However, is it negative or positive? Of course, it's going to be negative, which we accounted for in our equation. So the answer is going to be minus 100 kilojoules. And since 3 significant figures, our answer already has 3 significant figures. Let's go next. Calculate the heat of reaction for the production of CO2 using the given equations. This is very simple. Hess's law also, very straightforward. We look at the final equation and then we compare it how we can reach that. So we have CO on the left side. Over here, CO is on the right side. So we're going to have to reverse this equation. So let's reverse it. We're going to get CO gives us C plus half O2. And then the delta H, we're going to reverse the sign. It's going to be positive 110 kilojoules. And then we're going to copy down the other equation. C plus, which is carbon, plus O2 gives us CO2. And now if we add both of them, the C's will cancel, the O2 will cancel, we'll have remaining only half O2. So we're going to get CO plus half O2 gives us CO2. And we did nothing to this equation, so the delta H of it will remain the same as minus 393 kilojoules. And we added them up, so we summed both of those up. We're going to get minus 283 kilojoules. So minus 283 kilojoules. 3 significant figures, 3 significant figures. Rewrite the equation expressing the coefficients as the smallest possible whole numbers. This is our keyword, smallest possible whole numbers, and express the heat of the reaction as a term in the reaction. So let's first look at the heat of the reaction. So since it's negative, delta H less than 0, what did we say? We said it's going to be an exothermic reaction. And whenever you have an exothermic reaction, the heat will be released. So if it's going to be released, we will find it in the products. So basically, and since we only have one decimal, which is half, if I want to remove it, I multiply by 2 the full equation. So it's going to be 2C, and don't forget to put the state plus O2 gas, because 2 times half is 1, gives us 2CO gas plus, now remember, if I multiply the equation by 2, I also have to multiply the enthalpy by 2. So 110 times 2 is going to be plus 220 kilojoules per mole. And you see how I put it in the product side? Because it is exothermic. Write the reverse reaction without including the energy value. So we don't have to look at the energy value, just reverse the equation. So SO2 gas gives us S solid plus O2 gas, and make sure it is balanced. Here it's already balanced. However, in the exam they might not get you the equation balanced, so make sure it is balanced first. Determine delta H of the reverse reaction. Remember, if we reverse the reaction, we just change the sign of the delta H. So it was negative 297, it's going to be positive 297 kilojoules. 3 significant figures, 3 significant figures. Okay, this is the same question as we did before. However, they just gave us different values. So delta H, heat of combustion, equals to minus Q over N. However, this is not the specific heat capacity because we don't have any mass. So it's just going to be C times delta T over N, which is the number of moles. So it's going to be 5 times 10 to the power of 3 times 7 over, how do I find the number of moles? Mass over molar mass. How do I find the molar mass? So I have 12 times 2 because we have 2 carbons plus 1 times 4 because we have 4 hydrogen. So 24 plus 4 is going to be 28. 3.5 divided by 28 is going to be 0.125. So 0.125. And then if we solve it, we're going to get 35 divided by 0.125, which is going to be 280 kilojoules per mole. So heat of combustion, don't forget the negative sign. Please guys, make sure in the exam to put the negative sign. So it's going to be minus 280 kilojoules per mole. Okay, don't forget the negative sign. And finally, last question. Calculate the heat change when 3.2 grams of methane is burned in excess oxygen. Give your answer to 3 significant figures. Okay? Here it's exothermic, of course, because we're burning something. So what we have here is ethane. We have 1 mole of ethane releases minus 819 kilojoules. We want to know 3.2 grams. So first step, directly find the molar mass to find the number of moles. So number of moles is mass over molar mass. So the mass is 3.2 over the molar mass is going to be 12 plus 4, which is going to be 16. 3.2 divided by 16 is going to be 0.2 moles. So 0.2 moles of ethane. We want to find how much energy is released. Basically guys, just cross multiply. So 0.2 times 819 is going to be minus 163.8 kilojoules. However, this is 4 significant figures. They're asking for 3 significant figures. So I count 1, 2, 3, put a line. Is this number 5 or greater? Yes, so I'm going to round up. So I will get minus 164 kilojoules. And that is it. Thank you guys for watching. Best of luck in your exam. And don't forget, when you're done with your exam, leave a comment down below of how many mistakes you got. Hopefully we're going to see many hundreds in this exam. Thank you guys and see you soon.